All right, so let's talk about your final paper that we might have forgotten about. And actually, I want to start by handing out, so did people grab the writing center guide here? You didn't grab it, just raise your hand. And so kind of the main theme of everyone's paper is the citations were all over the place. And so I handed out the style guide. Oh. But then if you just go to like ACS style in your search engine, so there's a couple of things that'll come up. So the American Chemical Society, they have a guide. It's kind of behind their paywall, so I'm not sure how much you can see at home, although it should be open access, at least some of it. And it's been really slow. But there are other ones that might be useful. What was I looking at? So there's all these like citation generator too. So you can use kind of these tools to help you get it in the right format. And so this link, and I can post this link to Blackboard or something, but it gives you like journal article and then the examples to how you should format the name, and then of course the name of the article. The journal is italicized, bold the year, italicize the volume, and all that good information. So this is a good resource for formatting, and that's similar to what I handed out. But then the other kind of theme is that there are all sorts of like weird in-text citations. And so if you look at that guide that I gave out, there's kind of two best methods for how to do your citations. And so I would either pick the superscript method, or you could do numbers in parentheses. And so the way you kind of set it up is, you'll have your text or whatever, blah, blah, blah. Maybe you have your intro paragraph. And so if something like heavily references a source, then you can put a little superscript. And you don't need to like name it or something. You just, describe what's going on, your intro, blah, blah, blah. Do a little one. And then if you look at the Writing Center, so it doesn't matter what you call your works necessarily. So you can call them references, or I usually just use the term bibliography for kind of just standard research papers. But then you have your bibliography, and so that's numbered, corresponding to whatever number there. And so depending on your program, so there's like different ways to track these references. Otherwise, you just kind of have to do it manually at the end. But now that you've kind of had a rough draft, and maybe you know all your sources, you can of course add some more, expand. But then you have your sources, alphabetical order, all that good stuff labeled 1, 2, 3. And then you can cite them in the text, 1, blah, blah, blah. A study was done. And then if you look at how to talk about it, so you don't really want to be like, oh, in this article it discussed, but you could say like, oh, Brown and his associates. And so it says in this kind of Writing Center guide, like how to cite several authors. So you could say Brown or Chen, or if you have like multiple authors, you reference just one of them and say et al. And those are ways to kind of reference that, and then you put the number after, again, either superscript or parentheses, and correspond that to the bibliography. So that's the cleanest way to do it, and so you're not putting like large citations. So I don't really like the author date style where you have it in the text. But yeah, just try to keep it clean. So that was my main criticism. And then I wanted to hand out people's papers. And there are still a few people that I need to correct. And so I might like ask you guys individually because I might have lost your paper and walked away, or it is somewhere in another stack. But I put a bunch of comments to hopefully help you make another paper. Oh yeah, did you turn in a paper? Manny, I need you to print me another copy because it grew legs.
Okay.
Or I could look at home again. Yeah, so Cassandra, you didn't send me a paper, right? Did you, Sierra? And then Eve, I have your paper printed. Nikki, I think, I remember reading your paper. I don't know where it is. So if you could print me another one, that would be awesome. Otherwise, I'll look around in my stacks. I know you did one.
Oh, that's really good.
I know. I was slacking on this. I got
I
behind.
mean, yes, I did do.
But yeah, and there are other people who gave me drafts, so I will do those. Okay, I have a bunch of other papers to hand out. Actually, let me hand out exams before people walk off, like Tuesday. And so if you walked off Tuesday, and I lost my pen. I have too many papers. So if you walked off on Tuesday and missed your exam, I have it. But I also wanted to say that we are doing corrections for 50% credit back. And so if you have those, I would love those. Obviously, if you haven't gotten yours back, you haven't gotten a chance.
So you put stickers on them?
No. All right, so hopefully everyone that is in class got an exam back now. I have more papers. All right, so I'll hand more stuff back. Excellent. Any questions about anything?
When is the final paper due?
Just at like the end of the quarter, so I think the quarter ends June 17th.
Okay.
I can't remember, let's pull up my syllabus. Because I might have asked them to be due like the week before. Oh, I did not put the paper on the syllabus, wow, oops. So yeah, I should add that apparently. So I would like it if it was on the 10th, week 10.
Okay.
So maybe should I offer like extra credit, 5+ points if you turn it in early? And then if you turn it in by the 17th, still get credit, but. All right, let's do that. So we'll do extra credit if you turn it in by the 12th. And then make appointments with me if you want help like rewriting your paper, restructuring. I try to put like some chicken scratch notes on people for how to kind of like redo their outline. But if you can't read my handwriting, then I'm more than happy to sit down and talk about it.
That's the Monday of the last week, right?
Is it the Monday? I thought it was, I was going for like, I don't know what day.
Yeah.
Oh, you're right, it's a Monday. That's fine. So yeah, if it's due by the Monday plus 5 points, that gives me plenty of time to grade it. Otherwise, I will accept it normal credit after and up to the due date, so please don't want to go past June 17th. Let's see, anything else? Oh, we decided, so Dorothy and I decided to just skip last week's quiz, so you probably haven't tested and quizzed enough, so you don't have to worry about making that up. I said I was going to hand it out, but Dorothy wanted to give you all a break. Any other questions? We can look at our syllabus too as we kind of barrel towards the end. And so I have the lab for this week printed out, so we're doing electrolysis. And so up until week 10, we'll just be doing our regular labs now. And so these should be really fun labs, especially when we get into this one-pot one, and the aspirin synthesis is super fun.
What about the soap?
You want to do soap, we could do soap week 11. The only thing about the soap is we would have to bring our own molds probably, is of the curing time. So I don't know if people want to bring in, like it doesn't even have to be fancy. You can use like yogurt containers as molds, like that's what I've done before.
Or like a cake pan?
Just as long as it's not metal.
Come on.
Yeah, not, so you can use anything just as long as it's not metal.
Oh, okay.
Yeah, because the metal will react with like the residual sodium hydroxide, potassium hydroxide. But anything like plastic, silicon, all that's fine to use as soap molds. So yeah, if you really wanted to do a soap thing, if we like brought some supplies, we could do like a class soap. And I could probably supply like the sodium hydroxide at least. And then if we like pull in as a class, we can bring together like essential oils. And the thing with like soap is it's really like your preference. So that's why I say like bring in your own oils. I can bring in a couple things, but you know, like do you want your soap to have olive oil, coconut oil? Like, you know, if you're vegan, you're going to be more strict about the oils that can go in, or otherwise it could be like Crisco too, or you could use, you know, you could go crazy with soap making. So you could use like animal fats too. So it's kind of, so yeah, we could do that as a fun just lab.
I mean, it's fun, but it's also like useful and informative. And it does like, I mean, it does follow like chemistry principles. I don't
Yeah.
make soap at home because I don't understand the chemistry, or at least I didn't. So I mean, all
Yeah.
joking aside, I know we're asking.
No,
for
we
soap a
should,
lot, but, like,
I'm totally down to do it. It's just whoever wants to do it will come in, take over lab, talk about soap recipes, trade oils.
I mean, it helps dispel the like fear about soap that has lye in it.
Yeah.
It doesn't have to be scary, apparently.
Yeah. All right, so before we dive into our, I feel like the end of the year, by the way, is kind of like our hodgepodge chapters. And so from here on out, it's going to feel hodgepodgey. And so I'm going to go back and finish up our e-chem, so relating it back to potential. But then after that, it kind of becomes like fun facts, the class, and then we get into like more O-chem as well and some transition metal. So hopefully it should be a little more fun too than all like just the dry math we've been doing over and over again. All right, so let's see if we can look back. Let's see, so where did we leave off here? So let's practice, let's warm up, see if we can practice some of these calculating cell potentials or predicting. And so let's look at these two reactions. And so this one says without calculating the E cell. But feel free to calculate it for your own sanity. But go ahead and analyze these two reactions. Will these redox reactions occur? Might have to dig back in your brain. What does that mean? We'll go over it. have this. I could also try to make more paper copies. Okay, I found a blue one actually, if you wanted. I know there's too many reference charts and everything. No, oh, the problem, sorry. Got what we're doing. I need like a way fancier setup, like 2 projectors, like 1 reference screen. I can dream.
They have one of those downstairs.
Where?
So you know the study room on the 2nd floor in the corner? It's their classroom right next to it that has dual screens. It's pretty nice.
I don't know if it would work with my setup, but I'll have to check it out.
I mean, I think it's a smaller classroom, but like there's a number of people who come to class now. Yeah, there's a lot of.
So what do we think about A? Do we think it'll be spontaneous, non-spontaneous? So I would agree with you, but why?
So iron solid becomes Fe2 plus 2 electrons. And how do you say that, the volts?
Yeah, the electron volts or electron potential.
So the electron potential is 40.45. And magnesium 2 plus 2 electrons becomes magnesium solid. And the electron potential is negative 2.37. So it's negative 1.92. I don't know if I did that right, but.
Yeah, so that's one way to do it mathematically, and so that looks good. And then, is there a way we could not do math? And so I like the math way personally, like, I'll just say that. But was there another way to determine that? So which one has to be the anode again? So anode is, yeah, exactly, where oxidation is occurring. So oxidation, that means it's going to lose electrons. So it has to be some metal that wants to lose electrons. And so looking at this one, how it's set up, right? Iron's the one that's undergoing oxidation, losing metals. But then if we look at our chart and compare it, and so right down here, there's stronger reducing agents, meaning that these are really oxidizing agents, right? They want to, or and this means they want to be oxidized, excuse me. They want to be oxidized, right? But who's lower, magnesium or iron? So magnesium. So this is the way to go without math. So magnesium is lower. So this means that this one has more of a tendency to undergo oxidation. So that would be highly favorable. And we know, right, that those metals want to give up those electrons. Hence, their low reduction potentials. And so that would be another way to see. And so I'll just put that in parentheses. So magnesium is lower, so this should be the anode. But the way that this is, the equation is shown here, right, iron is acting as the anode, so that doesn't work. Awesome, so 2 ways to determine that. Did we get a chance to look at B? I'll give everyone a minute or 2 to look at B, watching the chat too. So what do we think about B? What are we thinking, spontaneous, non-spontaneous?
It would be spontaneous, right?
So why do you say that?
PV is above.
So PV is above iron, so then going back,
Why is this not?
no, you're correct, because then, so iron's below, which means it should be the anode ideally. And so that's what's going on, right? It's giving up electrons. So we can tell, right, so it's undergoing oxidation. And so it's lower, so yes, it is spontaneous. And so let's always double check ourselves with the math, of course. that's always a good way to check our sanity. And so let's see, so if we look at the potential for iron solid to iron 2+, so we had that, so that's still 0.45, correct? So let me write that out. Oh, I want green. So Fe solid, Fe2+, so 0.45. And so let's get the value of lead. Where's lead? So then lead goes, so this is 2+ plus 2 electrons gives us lead solid for negative 0.13 volts. So lead 2+. And so add those up, so it's still positive. So small potential, but still positive, so exactly like you said, spontaneous. Oops. Yes.
Is that calculating the E cell? Like, is that what we did?
Yeah.
Oh, okay, so I'm sorry that I didn't follow the instructions.
Yeah, so I mean, it told you not to do it that way, but I mean, really calculating the E cell potential makes me feel safe. Like, this is the way I like to do it. Even if you can look at the metals and see which one's lower, like, it's always good to check your sanity, write out the equations, and add it up. At least that's my opinion. I agree with you. Like, math is always the best way. And so finishing up this chapter, so now we can also predict whether a metal will dissolve in an acid. So of course you saw this in lab. So some metals dissolve in acid, and that is a case if the reduction of H+ is easier than the reduction of the metal, and if their ion reduction reaction lies below H+ on the table. And so you saw that with your activity series that you kind of made in lab. And then almost all metals will dissolve in nitric acid, and that has a nitrogen reduced rather than a hydrogen. And so that means like gold and platinum can also dissolve in what's called, it's shown here as nitric acid plus HCl. And so this is what's called aqua regia. I don't know if y'all have ever heard of this. So aqua regia. And it's a 3-to-1 ratio of HCl to nitric acid, but safety time. So you would never want to store a solution. So it's the way you deal with it is you usually like make it and then use it to clean, and then you neutralize it. So you never want to store it because eventually, especially if it's like, sealed up and tight, it could build up pressure and explode. And I've never had that happen to me personally, but I knew of another grad student who they were just happily working away in lab, and next thing you know, there was a giant explosion because someone had left an aqua regia solution just sitting under the cabinet, and it exploded randomly. So luckily they were not harmed or anything by it, but not a stable solution. So that's good to know. And so the last little bit that I had kind of alluded to on Tuesday was that we had to bring everything all together. So relating good old K, equilibrium constant that we've been calculating, and then how to relate that to G, of course, which was whether reaction will actually occur or not with Gibbs free energy. And so this is kind of condensed what you need to know for this chapter. Kind of how to convert between them. So you can see we can calculate delta G by these two methods. And then now we can relate our cell potential to delta G. And of course also get back from cell potential to our equilibrium constant. And so let's define what is all in these formulas. So again, delta G is negative RT times ln K. So this was from chapter 24, I believe. And so right, R was at 8.314. T was, of course, in Kelvin. And K is equilibrium. So same equilibrium constant that has been haunting us now, it feels like. And so we learn how to calculate that. And so now we can bring it and relate it to cell potential. And so N would be equal to the number of moles of electrons. So however many electrons are involved in that transfer. And then F, we have a new constant now. So this is Faraday's constant. And so this is relating how many coulombs per moles of electrons. So there's moles, moles cancels, so it gives you coulombs, and times your cell potential to get you to delta G there. All right, so now we're going to practice. So use your electrode potentials to calculate your delta G then for this reaction. And so at least get started on it. See if you can calculate, right, your E cell. And then maybe you could figure out how to do delta G. Just pay attention, of course, to how many moles are involved in this, moles of electrons are involved in this reaction here.
So are tabulated electrode potentials the standard reduction potentials?
Yeah. So did you already calculate your cell potential?
No, I have to copy the whole problem down because the PDF is not legible. So it took me up to.
So what was the reduction potential of this half? So bromide to bromine? Negative 1.07 volts. And then what about iodine plus 2 electrons to get iodide? So 0.54. And so then what do we get for overall cell potential? And so then is this spontaneous? So not spontaneous from our cell potential. And then, so let's also calculate our delta G. And so I'll just rewrite our formula. I'll try to stick to green. And so we said delta G was equal to negative NFE. So we just got E. And then what is N here? How many moles of electrons are involved? So 2. And then F, of course, was our Faraday's constant, so 96,485. Times our cell potential. And so volts, by the way, is equal to joules per coulomb, so that's where your units come into play. So everything will cancel to give you joules as your final answer.
Can I ask you a real stupid one while you're waiting for that to warm up? So is it 2 moles of electrons because we had two bromines or 2 iodines, but they've exchanged, like each mole exchanged 1 mole of electrons? Is that like, how do you figure that? How do you figure out that you have 2 moles of electrons?
Yeah, since there were 2 electrons involved in the process, and yeah, for like what you were saying, the 1 mole of iodine, use 2 electrons, and of course you get 2 iodide because they're splitting, but it's just basically how many electrons were involved in that process. And so when I just punched it in, I ignored the sign since that canceled to give me positive. And so now I have something like this. So 1, 2, 3, 4, 5. And so delta G is equal to 1.0. I was rounding to 1.02, I guess. 1.02 times 10 to the 5th joules. And of course, this also tells us that it's non-spontaneous. So of course, just reminding yourself that G has to be negative for it to be spontaneous. Let's head here. And so let's see, looking at the rest of the chapter. So now this is what's called the Nernst equation. And so this is just a short kind of derivative of it. So they just showed here, so you started with your Gibbs free energy is equal to delta G plus RT ln Q. So that gives us to here. So just substituting in for our equation for G, for Gibbs free energy. Then we're given that our cell, so then our E cell then would be equal to our cell potential that we calculate minus RT over NF times ln Q. And so Q is, of course, your snapshot then. R is back to this 8.314. F is Faraday's constant still. N, number of moles. And then this is natural log here, and if you convert it to log, this gives you your Nernst equation of your E cell is equal to this, so your cell potential minus 0.0592 volts over your moles times your LNQ. And so now let's look at these kind of concentration cells. And so it is possible to get a spontaneous reaction when the oxidation and reduction reactions are the same, as long as the electrolyte concentrations are different. And so the difference in energy is due to the entropic difference in the solutions. And so the more concentrated solution has lower entropy than the less concentrated solution. And so that means that electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. So that's kind of interesting. And we don't deal with concentrations like not 1 molar a lot in our kind of theory of this, but this is just, it's still really interesting, and you can kind of experiment with this too. And so that means that the oxidation of the electrode in the less concentrated solution will then increase the ion concentration of the solution. And so that means the less concentrated solution has the anode. So something else to kind of keep in mind. And so that means that reduction of the solution ions at the electrode in the more concentrated solution reduces the ion concentration. And so that makes the more concentrated solution the cathode. And so this little depiction is kind of a good example of what the heck we're talking about. And so just looking at our standard conditions here, so you have copper solid and copper 2+ solution. And of course, the same thing is being used as the anode and the cathode. And like we would expect under standard conditions, right, 0 voltage makes sense using the same metal, so your reduction potentials cancel out. But now if we look at these non-standard conditions, so we have a 0.01 molar solution on our left side, so our anode, and then a 2 molar solution on our cathode. And so let's reread these because this kind of helps. Okay, now let's put it all in context. So oxidation needs to occur at the anode, and it said we want the less concentrated solution since we're making ions. Excellent. So just double check your sanity. All right, that looks good. Less concentrated serving as my anode. Then I have a more concentrated solution serving as my cathode. And so then that gives us our reduction potential. Excuse me. Just looking if there's anything more we should talk about on this chapter. Sorry, I just feel like I'm missing sections on this notes. My notes got scrambled. I just don't know why this practice problem isn't in your notes. let's do this practice problem. I guess I'll have to write it out. So we'll go through it together. Actually, I'll just start a new page. So let's determine our cell potential for an EChem cell based on the two half reactions. And so you're given, so we have an oxidation reaction. And so this is copper, solid metal, going to copper 2 plus. And this has a concentration of 0.01 molarity. And our reduction side is looking at the permanganate. And this is a 2 molar solution, plus 4 H plus, so 1 molar, plus 3 electrons goes to manganese 4 oxide, plus 2 equivalents of water. And so there's a couple issues already. All right, let's walk through it together, because I don't know. So what's our first step looking at this? So let's start off by getting just our standard cell potential. So what's the cell potential of these two reactions? Negative 0.34. And then this one's hard to find sometimes. Should be there. Oh, I think it's up here, if you haven't spotted it, like towards the top of your chart. So it's a permanganate plus 4 H plus 3 electrons gives you manganese 4 oxide plus 2 water. And so that's 1.68. And it's now we just, again, this is just your standard cell potentials. We're not looking at the concentrations yet or anything. There we have our cell potential, so 1.34 volts. And so if we want to relate it to our Nernst equation, so let's go back for a second. So what was our Nernst equation? So E cell equals our standard cell potential minus this 0.0592 volts over N times ln Q. And so I'm just going to rewrite that for a second. So what the heck are we trying to find? We're trying to find this E cell. And so we found our standard E cell potential. So this is your standard E cell potential, standard conditions. Now we just need to plug in the rest of this. And so what's going to be the end, though, in this process? And so I kind of highlighted the tricky part. So how many electrons are going to have to be floating back and forth to make it the same? So 6, exactly. So N is 6. And so we have our E cell. Now how do we get Q again? What's Q? So let's generalize. So remember, Q was at least something, right? Products over reactants. And then when we did these, though, right, they always have to be some sort of solutions, some sort of concentrations. And so looking at what we have going on, so it looks like our products are going to be copper 2 plus, right? And then we don't care about the manganese oxide, so that's not aqueous, so that's fine. Just ignore that. And then our reactants then are this permanganate species, so we have the concentration of that. And we have our H plus ions, so we have that concentration. Except the only thing we have to be careful of is how many equivalents we're using of these. So if we had 6 electrons, so you're correct. And so if we have 6 electrons, what do we need to do to this oxidation equation? So multiply it by 3, so now this is times 3, which means that this copper in our expression is going to be cubed now. So Cu2 plus cubed in our Q expression over. And so what multiplier do we need to put on our reduction reaction? So 2, and I saw fingers of 2. Chad, if you're still alive, you could join us, put 2, 3, no clue. And so if this is 2, that means this becomes 2 times 4, so hydrogen has to go to the 8th. Luckily, I think it's 1, so we don't have to strain ourselves on our math. And so now we have something that looks like this, just our general expression. And then we'll use these concentrations that we were given to solve for Q then. And so now I'll go ahead and do that, or at least write in what we're putting. So in the problem, we said we had a 0.01 molar concentration of copper 2 plus on our anode side. So that's why I plugged in 0.01, again cubed, since it's times 3. Then they told us for our reduction side, manganese was a 2 molar concentration. So we can plug in that 2, and of course that gets squared. And then hydrogen was just 1 molar. So luckily that doesn't matter, but that gets to the 8th power. And so now we're ready to plug it in then. So first I'm going to solve Q, I guess. And so now I'll just write E cell. And now I'm just plugging in numbers. And so y'all can tell me what you get as well. So double check my signs and everything. But then I have that our non-standard cell potential is 1.34 plus 0.0651. To give us a 1.4 potential. Again, if someone can double check just that I plugged everything in correctly with this log, that would be much appreciated. Do we get same answer, different answer? Okay, at least got one thumbs up. Another thumbs up for the answer. Any questions on this, or? So how do we feel about our Echem chapter? So I think we finished Echem. Any questions on it? So you'll at least get to play with some more Echem stuff in lab this week, so that might help kind of solidify some fuzzy things. But if there are no questions, then I'll probably want to shift now and at least start our, what I'll call our hodgepodge chapter.
Can I ask real quick, on the oxidation of that problem, do we make it a negative 0.34 because it's being oxidized? Because in our chart, it shows that it's a positive 0.34.
Yeah.
Okay.
Yeah, so you flip the sign to match whatever way the reaction's going. So
Perfect.
with the problem, since it started with copper solid, that means we have to flip this,
Okay.
and if you flip it, you flip the sign.
Okay.
Yeah.
Thank you.
Other questions? All right, so now let's look at this chapter. So we're looking at kind of radioactivity, and then we'll transition to OChem. So it's kind of all over the place, but have we talked about radioactivity in this class before? I feel like we already talked about this.
Just the like math.
Yeah, I thought I remembered that. I feel like we talk about the exact same thing again now in this chapter. I'm not sure why that is. I need to look at the book chapter order again. But so this might be a refresher. Oops, hang on, this is not. Oh, I don't know. So I think we've seen this before, but radioactivity is the release of high energy particles and or high energy electromagnetic radiation from the nucleus of an atom. And so some other fun things that you can do. So does everybody remember that chart of the nuclides that's in lab? I don't know. I'm sure you guys have seen it. Maybe not paid attention to it. It like lives in the far corner where the tanks are. Well, there's lots of cool like online versions of it. And so this is kind of one of those interactive charts. And so I can post a link in the notes or maybe make an announcement, but this is kind of fun to play with. And just kind of, I mean, you could spend forever kind of looking at this, but you could look at gold and look at what type of radiation. So looking at this, we just want to look at gold, and then they're kind of color-coded to what kind of radiation they tend to undergo. But looking at the main ones, so we could look at like alpha, for example. It's a little slow. Come on. There we go, double click, sorry. So if you double click on whatever isotope you're interested in, so now this is gold 72, and then it gives a half-life of it, and then whatever decay mode, so this one only undergoes alpha decay, and then of course you can see all sorts of fun stats as well. So that's something fun to play with. And so looking at radioactivity, and so just to be clear, right, we're not really sure why certain isotopes are radioactive or not. I think we've kind of touched on that before. It's just sometimes, especially as the neutrons start to outweigh the protons, they just tend to become inherently unstable, and then they decay, and they decay, of course, by different modes. And so again, that's why I encourage you to play with this, so you can check out all the different isotopes. And so each row is a different element. You could really just have way too much fun playing with that. And so what's also kind of cool about radioactivity, and a difference from chemical reactions, of course, is that your radioactive nuclei spontaneously decompose into smaller nuclei. So, right, we make new atoms, which, again, that's not what happens with chemical reactions and is a big difference. And so that process is, of course, radioactive decay, and all radioactive nuclei are considered unstable. And so the parent nuclide is the nucleus that is undergoing the radioactive decay, and then the daughter nuclide is the resulting or new nucleus. And so anything with 85 or more protons is radioactive. And so these are the three main types of decay, and then we'll talk about how beta can either be beta positive or beta negative. But the main ones are alpha, beta, and gamma. And so alpha particles, this is just a helium atom over here. And so anytime you see that alpha, that means you're releasing helium. So it has a charge of 2+ and a mass of 4 atomic mass units. And let's see. And beta decay, so this can be, they usually have a charge of -1. They can also be positive and have a positive kind of, be a positron, and that would also have negligible mass. So this is electron-like. And then the last form of radiation is gamma. So this is light energy, and so it's not a particle and it does not have mass. And so in addition, you have positrons. So positrons is also known as beta decay, but positive. So you could see those kind of terms used interchangeably. And then you also have a different process called electron capture. And this is when a low energy electron is pulled into the nucleus. So that's a little different, and we'll look at that as we go through them. So if we look at alpha decay, And so again, the alpha particle is the helium nucleus. So anytime you see alpha decay, you know this has to be one of your products, at least one equivalent. And so one of the most, I guess, famous examples is the decay of uranium. And so this is used in part of like nuclear reactions. And so it goes from 238 uranium to 234 thorium. And of course, part of the new technology of nuclear power plants is how to convert this thorium to something useful. That's research area, and I think that they have accomplished that. And of course, you get an alpha particle. But the next question is, well, how do you know that this was a product? And I think we've covered this since we've done the math before. But if you recall, right, you had to add up all your total mass, and it has to be equal on each side. So if you started with 238, then your total mass on your product side also has to be 238. So as soon as you hear uranium 238 is experiencing alpha decay, you can just do, well, 238 minus 4 gives me 234, so that's a mass. And then 92 minus 2 gives you 90. And then, of course, you just look on your periodic table to see what element 90 corresponds to. And so alpha is the most ionizing but least penetrating. So you can be easily protected from alpha decay from like your clothing, so paper or light cloth. So all that will stop alpha particles. And so another common example is this radon-222, and it alpha decays, and again you can calculate that it would be 218 polonium. So let's go back. Where was that gold one? So let's figure out the product then of this gold 172. So if it undergoes alpha decay, so what's the product? So what do we get for our product? So what's the atomic number of gold? Yep, and it also said it over here. I don't know if anyone caught that. Remember, Z also means atomic number, but you can always look at your periodic table. And then, so we know it goes alpha decay, so I'm just going to write our alpha product. And so what's the other product then? What's the mass of my new daughter nuclide? 168. So 168, and then what's its atomic number? And so what element is that? Iridium. Any questions about this one? So relatively straightforward. And so then the next one to look at is beta decay, and I put a negative sign next to it because in this case, usually when your textbook is referring to beta decay, it means negative beta decay. But like I said, different textbooks can sometimes be beta decay more broadly, where it's negative or positive, or you can see like beta decay minus, beta decay positive. And so let's focus on beta decay negative first. And so this negative beta decay is a beta particle is an electron-like particle that is emitted from the nucleus when a neutron transmutes into a proton, which remains in the nucleus, and a beta particle. And so you can see this kind of mathematically, what's going on. And so, right, your total mass is 1 initially from your neutron. Then it explodes essentially to make, so right, neutrons are obviously neutral electrically. And so now you make your positive proton where your mass is, and it has a +1 charge. And then you get this formally 0, of course, so now it's electron-like, and then it has a -1 for its number since it's negatively charged, and of course they also have to equal back to what we started with, so our atomic number. And so again, beta decay occurs when an unstable nucleus emits an electron-like particle. And so beta decay, I want to erase this, is about 10 times more penetrating than an alpha particle, but only has half the ionizing ability. And so like heavy cloth could protect you, or probably like aluminum foil, lead foil. And so when an atom loses a beta particle, the atomic number will increase by 1, right, since it's formally kind of gaining a proton, so that increases our atomic number, and then our mass number will remain the same though. And so another common example is you can have beta decay from your carbon-14 nucleus. So carbon-14, if you remember, that's the one that's used for radioactive dating. So this is the isotope of carbon that's used. And so let's did anyone in here go on the Oregon Caves field trip? Man, all the Oregon Caves people skipped out today. Because in the Oregon Caves, they mention, I don't know if it was in the video at all, because I barely remember that video. It was a little dry when I watched it. I'm not going to lie. So I don't remember what was in there. But on the Oregon Caves tour, they mentioned that there were some like old fossils that could not be dated back with carbon. And so I was just looking. And so carbon radioactive dating, they say you can date between 500 and 50,000 years old. Just kind of fun facts and trying to relate things. And so this is a process that's going on when we talk about radioactive decay with carbon-14. And so it is beta decay. Yeah, so they said they found like bear fossils in the Oregon cave or something. They were super old or something ridiculous. But mathematically, if we write this out, so 14 carbon, and then if it's going to undergo beta decay, well, I know it's going to formally become an electron, no mass there. So then we can figure out our product. So 14. And I shouldn't have put that in there because I didn't know what it was yet. But so 7 plus a -1 gives us back to 6. So we know that's 7. So that corresponded to nitrogen. Let's see, what are other good examples? So another common example is phosphorus. So this will be our last one. So phosphorus 32. You could simply say undergoes beta decay. And I would put negative beta decay so you're not confused. But then, okay, let's write this out. So 32P, atomic number 15, that goes beta decay, makes that symbol, plus, so 32 is still our mass. And then what's the new atomic number of the product? So 16, and then what element is that? So sulfur. And so that's probably a good place to leave off, but then if you get really bored, you can look at, so on this one you have negative beta decay as like this pink color. So a lot of these on this side are all negative beta decay. Let's see, trying to find. So just a random one, so actinium 226. Again, you can look at the half-life of that and just really knock yourself out if you get really bored. So polonium 220, more fun facts. And this one doesn't even have half-life. So anyways, we'll end there. And so we'll pick up on Thursday with the rest of this chapter. All right. And I will stop this stream, so thank y'all. And then I will see everyone on Thursday for our usual lab time.